All right, so today we're going deep on something that's super important if you're aiming for those senior software engineer roles.
Yeah, especially when you get to those system design interviews. You
Exactly.
know, it's one thing to talk a good game about building scalable systems,
Right.
but when the interviewer starts digging into how you'd actually represent your data efficiently,
Uh,
that's where you can really shine and show you get the fundamentals.
oh, true.
We're talking about like literally the bits and bytes.
Okay.
Taking some piece of information, whether it's a user profile or like sensor data or whatever, and figuring out the smartest way to encode it in binary.
Because, at the end of the day, it's all ones and zeros that computers understand.
Absolutely. And all those ones and zeros, they add up fast?
Right. Think about all the data zipping around in a big distributed system.
Yeah, between microservices, databases, all of it.
You don't want it to be this bulky, slow-moving thing. You need it lean and mean, right?
Yeah.
So that's what we're diving into today. Two of the heavy hitters in the world of binary encoding.
Apache Thrift and Google's protocol buffers.
Ooh, yeah, two big names.
Born in the heart of big tech.
Right? Thrift coming out of Facebook and protocol buffers from Google,
Both open source now for quite a while, like since the late 2000s.
but still going strong.
Absolutely. And our mission today is to crack open the hood on both of them.
Okay.
See how they approach this challenge of efficient encoding.
And importantly, how do you, as a senior engineer, decide which one's right for your system?
And a core concept that both of these systems rely on is the schema.
The schema. Okay.
Yeah, it's like the blueprint for your data.
So you're not just throwing random bytes at the wall?
No, not at all.
Yeah.
The schema tells you what the data looks like.
Okay, so it's like a map.
Exactly. And you need that map both for encoding the data,
Right, so you can back it up nicely
but also for decoding it on the other end.
and make sure it makes sense when it gets there.
Right, so you can reliably reconstruct your data from that stream of bits.
So both Thrift and protocol buffers, they're like libraries, right?
Exactly, tools that help you do this encoding and decoding.
And it's all about taking your structured data
Yeah, think like that user profile we mentioned,
with a name, maybe some preferences, what they've been up to,
and turning it into this compact stream of bytes.
optimized for storage or sending it over the network.
Exactly, because every byte counts.
Okay, so let's get concrete here.
All right.
Let's say we're defining a person record
Okay, classic example.
in Thrift using their interface definition language, or IDL.
Yeah, Thrift has its own little language.
You might write something like this. Thrift, struct, person, one required string username, 2, optional I64 favorite number, 3, optional list string interests, 3.
Straightforward.
We've got our person with a username.
A favorite number, which is optional,
Right, maybe not everyone has one.
and a list of interests.
Now, protocol buffers, it also has its own way of defining schemas.
Similar idea, though, slightly different syntax.
And for our person, it looks something like this. Protobuf dot message person. Required string username, 1. Optional. Int64. Favorite number, each 2. Repeated string interests, 3.
Pretty much the same information, just laid out a bit differently.
Okay, so we've got our person defined in both systems. But what jumps out at me are these numbers next to the fields.
Ah, yes. The field tags 1, 2, 3.
This is where things get interesting.
Absolutely. This is key to how these formats get so efficient.
So those tags, they're like shorthand for the full field names?
Exactly, like little numerical nicknames.
Okay.
And here's the kicker. When you actually encode the data into binary, you only include those tiny tags, not the long names like username.
Interesting. So we're ditching the verbose stuff.
Right. That's one of the big reasons why these binary formats are so much smaller than, say, JSON.
Because with JSON, you got to write out the full field name every time.
Exactly. It's like sending a postcard versus a telegram.
Okay, I like that analogy.
Short and sweet gets the job done.
So let's actually see this in action.
All right, let's take our example person.
Our friend Martin.
Let's say his username is Martin. Favorite number is 1337.
And he's into daydreaming and hacking.
Good combo.
Now, Thrift's got a couple of different binary protocols.
Yeah, one of the original ones is called binary protocol.
If we encode Martin using binary protocol.
It comes out to about 59 bytes.
Okay, so not bad.
Not bad, but we can do better.
Right.
Now, if we peek inside those 59 bytes,
What do we see?
well, for each piece of data, there's a little marker saying what type it is.
Okay, is it a string, an integer, a list?
Exactly. And for things like strings and lists, which can have different lengths.
Right, you don't know how long they'll be ahead of time?
There's also a length indicator saying how many bytes to read.
So the decoder knows when to stop.
And of course, you've got the actual data itself, like the letters in Martin.
Encoded using UTF-8, right? The standard way for texts.
Right. And the point here is you won't find the actual word's username or favorite number anywhere in those 59 bytes.
Interesting. It's all about the tags and the type indicators.
Yeah, they're the secret handshake that lets the decoder figure out what's what.
Now, you mentioned Thrift can do better than 59 bytes.
Oh, yeah. They've got this other format called Compact Protocol.
Compact? Okay, so it's like binary protocol's leaner cousin.
Exactly, and it lives up to its name.
How so?
Well, if we encode our same Martin using Compact Protocol, it only takes up 34 bytes.
Wow, that's like almost half the size.
And in the world of data transfer, that can make a huge difference.
Right, especially if you've got tons of data flying around.
Absolutely.
So what's Compact Protocol's secret?
Well, it's got a couple of tricks up its sleeve.
Okay.
One is it's really clever about how it represents the field type and the tag number. Instead of using separate bytes for each, it often smushes them both into a single byte.
Okay, so it's packing more information into less space?
Exactly, squeezing every bit for all it's worth.
I like it.
And the other big win is it uses variable length integers.
Variable length. Okay, so not all integers are created equal.
Right, like if you've got a tiny number, it doesn't need a full 8 bytes.
Like our favorite number, day 1837?
Yeah, that can fit comfortably in just 2 bytes.
Interesting.
But Compact Protocol, it figures out the smallest number of bytes it needs for each integer.
Without losing any information.
Exactly. It's got this clever system where each byte has a bit that signals whether there's another byte coming for the same number.
Okay, so it's like a little chain of bytes if needed. But if the number's small, you can cut the chain short.
Right.
So even though Compact Protocol is using less space, if we decode those 34 bytes, we still get back our good friend Martin.
Absolutely. Same username, same favorite number, same interests.
Okay, so it's just a more space-efficient representation.
Exactly.
Now, what about protocol buffers? Where does it land in this size game?
Well, interestingly enough, it encodes our Martin in 33 bytes.
Oh, wow. So almost identical to Thrift's Compact Protocol.
Yeah, they're playing the same league when it comes to raw efficiency.
Okay, so they're both using some fancy tricks to get the data down to a similar size.
Right.
But are they using the same tricks?
Well, there are definitely similarities.
Okay.
Like protocol buffers. It uses field tags, type identifiers, and length prefixes for things like strings.
Right, like we saw with Compact Protocol.
But it does have one interesting quirk in how it handles lists.
Okay, lists like Martin's interests.
Exactly. Instead of having a special list data type like thrift, protocol buffers uses this thing called a repeated marker.
Repeated, okay.
Yeah. So for Martin's list of interests, the field with tag number 3 would just show up multiple times in the encoded data.
So one's for daydreaming and one's for hacking.
Exactly. Instead of saying, here's a list with 2 items, it's like, field 3 is this, and also field 3 is this.
Interesting. So it's kind of like it's repeating the field to indicate that it's part of a list.
Right.
Now, we've talked about how these formats make the data smaller.
Yeah.
But what happens when you need to change your data structure?
Schema evolution, the million-dollar question.
Right, because in the real world, things change.
Oh, constantly. You might need to add a new field.
Or maybe change the type of a field.
Or even remove a field.
And you don't want to break everything that's already using the old data.
Absolutely. So this is where understanding how these formats handle schema evolution becomes critical.
Especially for senior engineers who are designing systems that need to last.
Right. You need to think long-term.
Okay. So how do Thrift and protocol buffers handle these changes?
Well, the key to their flexibility lies in those field tags we talked about.
Okay, the numerical tags.
Right, because remember, an encoded record, it's basically just a bunch of encoded fields strung together, and each field is tagged with its number and its data type.
So the tag is like the field ID card.
Exactly, and this gives you a lot of freedom.
How so?
Well, you can change the actual name of a field in your schema all you want, because that name never actually gets put into the encoded data.
It's just for us humans to read.
Right. The computer only cares about the tag number.
Okay.
But, and this is crucial, you can never, ever change the tag number of an existing field.
Okay, so once a tag is assigned, it's like set in stone.
Exactly. Because if you change it all, the old data with that tag becomes unreadable.
Right, the decoder wouldn't know what to do with it.
It'd be like speaking a different language.
Okay, so what about adding a new field?
Like if we wanted to add an age field to our person, yeah, that's a common scenario.
How would that work?
Well, you'd just define the new field in your schema
Uh-huh.
and give it a brand new tag number 1 that hasn't been used before.
Okay, so every field gets its own unique tag.
Right, and the beauty of this is that older code that was written before this new field existed,
Yeah.
it can still read the data with the new field.
Interesting. How does that work?
Well, it'll come across this new tag in the data,
Huh?
but because it also knows the type of the field from the encoded data,
Right.
it can just skip over it.
Like it's not even there.
Exactly. It's like reading a book and ignoring the footnotes.
Okay, so adding new fields is generally safe.
Yeah, as long as you follow one key rule.
What's that?
You can't make the new field required.
Required. Okay, I see.
Yeah, because if you did, and then old code tried to read the new data, it would be like, wait, this required field is missing?
And it would freak out.
Exactly. So
Okay.
any new field you add after the initial rollout,
It's got to be optional.
or have a default value.
Even if the old data doesn't have it?
Yeah, the new code can still handle it gracefully.
Okay, so that's forward compatibility.
Making sure new code can read old data.
Right.
But what about backward compatibility?
Can new code read old data that's missing the new field?
Yes, as long as the new field is optional or has a default value,
That makes sense.
because then the new code can just fill in the gaps.
What about removing a field?
Like if we decided favorite number was a bad idea, sometimes you got to clean house.
How do you do that safely?
Well, you can only remove a field if it was optional to begin with.
Okay, so no required fields can be deleted.
Exactly, because otherwise, old code would be expecting that field.
And it wouldn't be there.
Right, it'd be like following a recipe that's missing an ingredient.
And then you've got a broken cake.
Exactly. And one more thing.
Mm-hmm.
Once you remove a tag number,
Yeah.
never, ever reuse it for a new field.
Okay, so those tag numbers are retired for good?
Exactly, because there might still be old data floating around with that tag.
Right.
And you don't want new code to misinterpret it.
Like thinking it's a completely different field.
Right.
Now, what about changing the data type of a field?
That's where things get tricky.
Like if we stored age as an integer,
Uh-huh.
but then realized we need a bigger integer.
Yeah, changing data types can be dangerous.
Because you can lose information.
Exactly. Like if you go from a 64-bit integer to a 32-bit integer,
Uh-huh.
you might chop off the top part of the number.
So it doesn't fit.
Right. It's like trying to squeeze an elephant into a phone booth.
Okay, so you got to be really careful with data type changes.
Absolutely. Always consult the documentation for your specific encoding format.
And think through all the edge cases.
Yeah.
Now, we talk about how protocol buffers handles lists with that repeated marker,
Uh-huh.
which is different from Thrift's explicit list type.
Right.
Does that have any implications for schema evolution?
It does actually. In some ways, it gives you a bit more flexibility.
Okay.
Because with protocol buffers, you can change a single valued field to a repeated field.
So from like one thing to a list of things.
Exactly. And it won't break compatibility.
Interesting. How come?
Well, because the repeated field, it's just the same tag appearing multiple times.
Right.
So old code reading new data with multiple values,
Yeah.
it might just see the last value,
Okay.
depending on how it's programmed.
But it wouldn't crash.
Right. And new code reading old data with 0 or 1 values,
Uh-huh.
it'll just see a list with 0 or 1 items.
Okay, so it's like it can handle both cases.
Exactly. It's pretty slick.
Now, Thrift's dedicated list type, it doesn't allow for that same evolution.
No, but it does have built-in support for nested lists,
Okay, like a list within a list.
which protocol buffers doesn't handle directly.
So it's kind of a trade-off.
Yeah, depends on what your needs are.
Yeah, one last thing about the schemas.
Huh?
Those required and optional keywords,
Yeah,
they don't actually affect the binary data itself, right?
that's right. They're more like rules for the code.
Okay.
It's the code generated by Thrift or protocol buffers
Uh-huh.
that enforces those rules at runtime.
So it's like a way to catch errors during development.
Exactly. It helps make sure your data is consistent.
Okay, so we've covered a lot of ground here.
We have
We've looked at Thrift and protocol buffers.
2 powerful tools for efficient data encoding
We've seen how they use schemas and field tags to make the data smaller.
and how they allow you to evolve your data structures without breaking everything.
And this is all super important for senior engineers
Absolutely, especially in system design interviews.
because interviewers want to see that you understand these concepts.
That you can think about data efficiency and schema evolution.
It's not just about picking a format and hoping for the best,
No, you need to understand the trade-offs.
and how these choices impact the whole system.
Right.
So here's a question for all you listeners out there.
Yeah, something to ponder.
How might your choice of encoding format, whether it's Thrift protocol buffers, or something else
Yeah.
impact the performance and scalability of a distributed system.
Think about things like how much processing power it takes to encode and decode,
Right.
whether there are good libraries for your programming language.
And how easy it is to manage schema changes across a bunch of different services.
These are the kinds of questions that separate the good engineers from the great ones.
Exactly. So keep those in mind as you prepare for your interviews.
And as you design real-world systems.
Because at the end of the day,
Yeah.
efficient data encoding,
It's not just about saving a few bytes.
it's about building systems that are fast, reliable,
Yeah.
and can handle whatever you throw at them.
And that's what we all strive for as engineers.
Absolutely. All right, well, that's our deep dive for today.
Hope you enjoyed it.
We'll catch you next time.
Until then, keep coding.